Okay, so welcome everybody to our centrifuge inauguration. I'm really happy to see so many of you here today for this very special day for us. Before I start, as you see this thing flashing, the event is recorded, so if anybody has any issue, please speak to our photographers so that we make sure that we don't do anything that you wouldn't like to be done. It's recorded, so there will be a video, some photos, so simple things. So we start with our program. We will start with opening addresses, then I will start with a presentation of the Geotechnical Centrifuge Center. After this, we will have presentations of some first experiments, some very short presentations. So you see some of the projects that are ongoing and some of the completed projects also that have happened since the last 1.5 years. And then in the end, before the apero, we will have a test flight with a surprise, which we hope we will like. And of course, we cannot have such an event without an apero. So then there will be an apero, but because there are so many of you who will have the lab visits, we have to have them in groups of 25, 30 people maximum. So these visits will happen in parallel to the apero. So we will be all together for half an hour, and then, I don't know if Eva is here yet, but Eva is responsible. There she is. So Eva, please. So Eva is responsible to take the groups and make sure that we follow the time. Okay, she has a very big bell. A big bell, this is especially for me to make sure that I keep my time. So this is it. This is the schedule. So now I would like to start with the opening addresses by calling to the stage Professor Ueli Weidmann, who is our Vice President for Infrastructure and Sustainability. It's a great pleasure to have you here to give his opening address. Ueli, the floor is yours.
I hope we are not so far away from the centrifuge because of the surprise.
No, we're safe here.
Okay, dear Ioannis, dear ladies and gentlemen, I'm very glad to give some welcome address on behalf of the Executive Board of ETHZ Zurich. And the whole research of ETHZ Zurich is in the micro area. And the whole research, no one department consistently sticks to large-scale labs. It's the Department of Civil, Environmental and Geomatics Engineering, and there are good reasons for this. What is the molecule for many academic disciplines is tens of thousands of tons of material in the construction area, or even more. This will not change in the future, and the projects are becoming even more challenging. Critical areas have to be utilized more and more frequently for construction. More and more often, infrastructures are built in the underground because space above ground is becoming scarce or protected. Buildings get more expensive, which increases the financial risk of damage in case of ground failure and earthquakes. In short, the best possible understanding of geotechnical properties is not only scientifically exciting, but also highly relevant to society and economy. Numerous valuable insights have already been gained from the centrifuge operated by Professor Sarah Springman. New dimensions are now opening up with the new large centrifuge. In Ioannis' appointment committee, where I took part, it seemed quite unreal to me at first when he mentioned a centrifuge of enormous dimensions at the University of Bochum, and even more surprisingly, that it would be available for free. Ioannis got the chair, and the idea became real. In 2017, the executive board decided to take over the centrifuge and to build lab facilities for around 5 million Swiss francs. The timing was perfect, as the HIF building, including the civil engineering test hall, being renovated at the same time. The underground space for the centrifuge could also be realized in a coordinated manner. The lab is organically embedded in the building and is located close to the offices and lecture rooms. At the same time, it was and is technically extremely demanding, as we are constructing now the HPQ building in the immediate neighborhood. This building is intended for the most sensitive physical experiments you can imagine, which don't accept any kind of noise. Just this much about the centrifuge itself. The diameter of around 9 meters required a concrete cylinder weighing around 300 tons for housing. We had to use the largest road crane of Europe for the installation. The maximum acceleration of 250 G led to inquiries from federal government as whether we were using the centrifuge for uranium enrichment. Construction of the lab began in May 2019. The first real test was carried out in August 23. The centrifuge is an invaluable addition to our scientific facilities, and I would like to thank everyone involved to make this possible. I would like to mention Ioannis and thank him for his initiative, the persistence, and the scientific advice. And I would like also to mention our project manager, Rainer Brandstetter, who not only managed the construction project professionally in terms of time, cost, and quality, but also developed a great personal enthusiasm. I'm now looking forward to the many other contributions, and I thank you very much for organizing this event, and I wish all of us a great evening and hand over to Sascha Puzrin. Thank you very much.
Speak directly.
Thank you very much, Professor Weidmann, for this nice introduction. When Ioannis asked me to say a couple of words, I had to promise that I'm not going to say anything embarrassing. So what are you going to do now? Shoot me? Well, almost 10 years ago, during his interview here, we asked Ioannis whether he would need a larger centrifuge. And he said, no, he is perfectly happy with what Sarah built. And then a couple of years later, he came to me and said that we can get a much bigger one for free. And like Professor Weidmann, I was not in the beginning very enthusiastic about this idea, because the only line I remember from Virgil is, beware of Greeks bearing gifts. Professor Weidmann told you how much did this free gift costed ETH. But I wonder whether the fact that we didn't get any proper salary increase in the past 5 years is somehow related to that. Even I had to fork out a tidy sum, which in the beginning was intended as a loan, but over the years looks more and more like a donation. But Ioannis made a compelling case. First of all, he said that when you bring visitors to the Institute, you need to show them something large and very impressive. Second, we will be able to say, my centrifuge is bigger than yours. And finally, he promised that we are going to have a great inauguration party. To be fair, he also mentioned something about research. But honestly, by that time, I stopped listening. Well, what we admire our Ioannis for is that he is a man of his word. And today, indeed, we are going to show you something large and very expensive. And I'm sorry, but our centrifuge is bigger than yours. But most importantly, I am really happy to welcome all of you to this exciting inauguration event, including the research part, because surprisingly, actually, Ioannis was meaning it, and he took it very seriously to use this thing for research. So welcome all of you again. Enjoy it, and Ioannis, the floor is yours.
Yes. Thank you both for your kind words. Thank you, Sasha, for not saying anything embarrassing. Okay, so we're very happy today, but of course this was a journey that was not always easy. So let's see the whole story. So first of all, I would like to say that today is not a random day. It's a very special day personally for me. It's the anniversary from the 30 years from the Kobe earthquake. The Kobe earthquake took place 30 years ago exactly, 17th of January of 1995. It was a huge earthquake that tested almost any kind of facility. The clock you see here is stopped at the time of earthquake. This you can find in Kobe if you go there. Why is this important for me? Because when I was a student at this time at National Technical University of Athens, and Professor Gazetas, and I'm very happy that Professor Gazetas, who was my professor at NTUA, is here with us today, made an amazing lecture about the Kobe earthquake, and this lecture changed my life, because this led me to the conclusion that this is what is for me, geotechnical earthquake engineering. So I didn't pick this day randomly, it's for this reason. So the Kobe earthquake did a lot of damage to port facilities, like the one you can see here. This graph actually is done by hand by Professor Gazetas himself. And you can see displacements of the order of 3, 4, 5 meters due to liquefaction and lateral spreading. Collapses of bridges, many different things. So it was clear at this time that there are many questions that are unanswered, and we need experiments to understand what is happening, to understand the mechanism of failure, to better design our structures. The Japanese took it very seriously, and after the Kobe earthquake, they made this huge shaking table, which is called ETHZ that you see here, 15 by 20 meters, and it can carry 1,200 tons. A real building in full scale can be tested in ETHZ. However, even with this huge shaking table, the maximum soil you can put on top is something like 5 or 6 meters. So when you are testing systems that have structure and soil, like we do, even with this huge shaking table, real scale is not possible. Even if it was possible, you know how much one test in this facility costs? Who can guess? It's about $1 million, $1 million. Okay, it's a huge facility, really expensive. So it's clear that for geotechnical earthquake engineering, for systems that include soil, foundation, and structure, this is not the way to go. The way to go is centrifuge modeling. And for those of you who are not, I mean, many of you know very well why we have centrifuge modeling. There are people like Luc, for example, who are very much experts in centrifuge modeling. But for those of you who don't know, I would like to explain why we need it. So here I have an example of a soil layer of 20 meters, a pile, like the ones that Labros will show you later. So if we take a soil element here at a depth of 15 meters, the stress level at this depth is a function of the weight of a soil that is above it. Okay. When we scale this problem down, let's say we scale it down 50 times, then, as you can see here, it's not 15 meters, it is 30 centimeters. So from 15 meters, we go down to 30 centimeters. So the stresses are much, much smaller. And this means that we have a different material. To put this very simply, this is the example I used to explain this to someone who is not an expert. When you go to the beach and you play with sand, you can make a nice sand castle. It's very soft. The same sand at 30 meters depth, it's something else. So the trick of a centrifuge is that it increases gravity. We reduce geometry 50 times, for example. We increase gravity 50 times, so we have equivalence of stresses. So this is how it works. There are two types of centrifuges. The one we will focus today is the new one, which is the beam centrifuge on the left, which has a swing where you put your model inside. You see it here in this nice video from RPI, from my colleague, Professor Abdun. The swing rotates following the vector of gravity. The second type is the drum centrifuge, which we also have here. This is the one that was established by my predecessor, Sarah Springman. This doesn't have a swing, and everything is smaller there. So when I first came at ETH in 2016, this is actually when Sarah Springman had just become rectorin, and this is why this chair, this position was open. This is a photo from a newspaper about the inauguration of a drum centrifuge some years ago. And actually you can see Markus Itten, a bit younger than today, but still Markus Itten, our centrifuge pilot, working on the drum centrifuge. So as soon as I came, we started discussing what can we do with a drum centrifuge, how we could model earthquakes. And the more we're discussing about this, we were solving one problem, and then we had 10 more problems to solve. So things were difficult. To model earthquakes in the drum, not easy at all. The space is confined, it's difficult. So at that time, we went to Eurofuge in Nantes, a conference on European Conference of Physical Modeling, Geotechnical Engineering, called Eurofuge also, that was organized by Luc Torel, who's actually here with us today. And there I met Jan Lauwe. And Jan Lauwe, he had just moved to Sweden as a full professor. He was here for many years, working with Sarah Springman. We met, and he told me a story. He said actually that what you see here, actually this newspaper you see here, had been in our laboratory well many years before this was even a thought. Okay, so this is from when the Bochum centrifuge was installed originally in Bochum. So I met Jan there. Jan had done his PhD working on this centrifuge, and he told me that it was decommissioned. It is in a storage somewhere in Germany, and maybe it would be a good idea to check whether we could get it for a very good price. Okay, so this is how this idea started, by meeting Jan in this conference. I also learned that today we have with us, where are you? Yes? We have the first ever PhD student that did his PhD working on this centrifuge. So this is also really nice to see. And we have also Jan Lauwe together with us. So I would like to invite Jan as a guest star, let's say, to tell us a few words about the history of a centrifuge, the previous life of a centrifuge in Bochum, and some nice stories from his experience and the experiments he has done.
Yeah, thank you, Ioannis, and congratulations.
Yeah.
And I put together some slide. As Ioannis said, I'm not the first PhD student in Bochum, but actually this is my second inauguration with the centrifuge. I just recall that as I started as a student assistant, one of my first tasks was helping organizing the apéro after the first inauguration. So it's not the first inauguration, I thought. And I digged out some papers, and the paper you see on the right side, that's when the centrifuge was ordered by the German Science Foundation in 1984. It arrived in Bochum at 1985, and at 1987, I think that, I'm not 100% sure, but I think that was the time where we had the inauguration. It was the first time that we reached 250 G with the machine. So that's how it looked like when it was built. It was built in Duisburg at Krupp, as written on the tin. And the lower picture, no, that doesn't work, how it looked like, but Ioannis had a photo of that already. That is how data acquisition looked like. So in the start, when I started as a student assistant, the data acquisition looked like on the right side. the control panel, also relatively old-fashioned compared nowadays. And then we changed the data acquisition. The data acquisition looked a bit more modern in the 90s.
15 more minutes.
Just some examples what has been done. Uwe Stoffers worked with tunnels. We had projects on diaphragm walls. This was a big diaphragm wall in Alexandria, which has been simulated in the centrifuge. We looked at piled raft foundations and several other questions. And one of the boundary questions I just want to mention is the mine shafts. That's the reason why we can create, or Ioannis now can create samples up to a 1.8 meter height. So there are a lot of things having been done. Another example, a more modern tunneling machine, which has been built by ETHZ shortly before I left Bochum. One of the specialties of the machine were that we did a lot of dynamic modeling. So not shaking table in the sense for earthquakes, but we had a lot of tests with actively dynamic loaded foundations in all type of directions, cyclic, torsion, piles, and shallow foundations. We also had impact dynamic tests. So we developed, for example, you see here, a shooting device where we measured deflections in a pile. And for that time, when you look at the data acquisition, the timing, we already had a very fast data acquisition. So we could do quite a lot of things with it. And then, and that's why I'm stressing this slightly, we were asked by an assurance company to look at a ship failure. And actually this ship came from Luleå. So exactly the place where I am now. So it traveled from Luleå, went down to Helsinki, tilted. There were some casualties. And we were asked to simulate that in the centrifuge. And to be able to do that, we built the first shaking table. So it doesn't look anyhow like an earthquake shaking table, but we put a basket on swings and loaded it from two sides. We could create kind of a lot of ship movements. And you see the application, a heap of iron ore which fluidized during the voyage and basically helped for the ship. You see the mass transport on the bottom right when this tilting happens. So we have a mass shift in the ship body. We also used this then for the first sort of liquefaction, real liquefaction test. And as it was just a master student or a Diplomarbeit at that time, we used very modern measurement equipment, colored spaghettis, cooked, which helped very nicely to show deformations. We also had some disasters or failures. So we built a cone penetration device, but then we reduced the size of the container, and at some stage the soil was getting too stiff, and we had a buckling failure in the CPT rather than we measured till the very end. Also, sometimes it was quite fun to work there. So here we're sitting on top of the old centrifuge center, putting envelopes in for the next inauguration for the second centrifuge in Bochum. And then, as Ioannis mentioned, it was stored and finally rescued, and now it's in Zurich. Thanks a lot. So.
Thank you, Jan. So after talking to Jan, we went together with Ralph, and I think Kostas Kassas was also with us. We went to Bochum and talked with a late Professor Sands and Dithard Konig, who is here with us today. Dithard, where are you? Ah, there you are. And actually we arranged that, yes, this is possible. We can get the centrifuge, not for free, at a very good price, very close to for free. But of course, as you will see the state at which it was, at this time it looked almost like Mission Impossible. But of course you need to put it somewhere, and this is not a small machine, so you need a new laboratory. So we started immediately doing a pre-design, let's say, of a new laboratory. And we had a lot of help from Andreas Galmarini. Andreas, are you here today? There he is, okay. So these are some of the drawings of the first design, as you can see here. So Andreas Galmarini helped us a lot with the first design. Then the location is always important. As Professor Weidmann mentioned, we have some neighbors which are very sensitive to vibrations. So there is a new physics building that is currently under construction, quantum physics building, and this building will have laboratories that are super sensitive to vibrations. So when we started, there was a fear that as the centrifuge is spinning, if there is some unbalanced mass, then this vibration may affect negatively the future tests that will happen in this laboratory. So this is how it will look like. It's extremely sensitive to vibrations. And at this point, trying to convince our colleagues from physics that this is not a problem, I asked Orestis Adamidis, and I think Orestis is here with us today. Orestis, yes. Orestis is today a professor at the University of Oxford. At that time, he was doing his PhD with Gopal Matabusi, that you see exactly below. And Orestis kindly spanned the centrifuge in Cambridge and did some measurements for us. And what did you measure, Orestis? You measured nothing, right? It was very close to zero, almost nothing. I was very happy. I came back with the measurements. I talked with our colleagues from physics. Is Gianni Blatter here? There he is. So I talked with our colleagues from physics. They told me, is it exactly the same machine? Well, the answer was, of course, no. It's not exactly the same machine. Ironically, it has exactly the same diameter, which I think is not a coincidence. But it's not exactly the same machine. Then they asked me, are we talking about exactly the same soil conditions? Well, you know, it's another country. I have no idea. No. So then they said, we believe nothing. Okay, so we were stuck. So then I thought of this idea of vibration isolation. It's an idea that has been applied in several structures for different reasons, usually not to isolate a spinning centrifuge from its surrounding, usually to isolate, for example, a building like this one from trams or railways that are passing by. So it's a bit the opposite. But I thought that this is an overkill. So at this stage, because, you know, centrifuge, if it's balanced, it should be balanced, the vibrations are small. It doesn't create a lot of vibrations. But then I spoke with Sasa, my colleague, Professor Puzrin, who advised me, this is what you need to do, vibration isolation, this is the only way that this project will go through. And this is what we did. With the help of Thanasis Agalianos, who is here with us today, and Kostas Kassas. Where is Kostas? There is Kostas. We did some preliminary analysis of this vibration isolation system. And here are the results of those analyses. You see on the left what happens if the structure is not isolated. On the right, you see what happens if it is. And on the graph below, also you see, in terms of velocity, in micrometers per second, very tiny velocities, you see the difference between isolated, the red line, and non-isolated. So this was convincing, I would say. There was a meeting, a very important meeting. So you see also here, at this time, the VCG level that you see, this was defined as the limit of vibrations we could have, and we were clearly below. So then the design was updated to accommodate this, sorry about the rocking isolation, it's not rocking, I'm confused a bit by our studies. This is not rocking, it's vibration isolation. So there was a very important meeting to approve this project, and Ueli Weidmann was there. Not only Ueli Weidmann, of course, representatives for physics building, and everybody was convinced that this will work, and the project was approved. So this was September 21, 2016. So the project was approved. Of course, the design was not fully done. Now, we come some years later. Now everything has been constructed. And I have here Dan Ixel. I don't know if Dan is here. There he is, Dan Ixel. So Dan Ixel did the detailed design of a vibration isolation system, but also a few months ago, October 2024, organized also some measurements. So we spanned the centrifuge, with various unbalanced masses and measure the vibration. And I have here some of the results. So you see here, the excavation for the physics building has been done, not completely, it's almost at the final level. And you can see here the results of the measurements. So the VCG level is up here, or up here for the vertical direction, and the measurements are down here. So we're clearly below the VCG level. We are a bit above from a newer, lower level, but we will fix this. Okay, so in general, I would say the vibration isolation system is fulfilling its scope. So hopefully, Gianni Blatter will be happy of having no vibrations negatively affecting his experiments. We start then with a refurbishment. That was in 2017, and I have here Ralph Herzog. I think Ralph is in the laboratory at the moment, right? Ah, he's here, so Ralph is here. A very crucial person for this endeavor, let's say. He's the head of all our laboratories and played a really crucial role for the development of a new facility, along with everybody else, because as you can imagine, this is a team effort, and there is a really big team. You will see, as I go through, you will be seeing faces, everybody that contributed. So this is how we started. This is when we went first time to Kreuztal. Have you ever heard of Kreuztal? Maybe Dietmar has heard of Kreuztal. It's in the middle of nowhere, somewhere in Germany, an industrial area. There was a storage, we went there and we found the centrifuge covered with some plastic sheets. We look very happy there, but Ralph clearly understood that this is really close to Mission Impossible. But of course, this is why we have Ralph for Mission Impossible. The hydraulic pump, the hydro motors, this was the condition when we first saw it. Of course, it was carefully dismantled and it was not in a destructive manner, but this is how it was. There was a company in Germany that had done the dismantling of a centrifuge, a company, big company, like 3,000 employees, I think. And we decided at the beginning to assign this company for the refurbishment. This made sense because the centrifuge could stay in Germany. This company was also in Germany. So they would fix it, refurbish, and then bring it directly here to install it. This sounded very good. About a year later, 2018, there were problems. Because at this time, the refurbishment should be more or less completed, but we were not getting a lot of progress reported. Okay. They told us that we need to have a discussion. They want to understand some details about the hydraulics. So we decided to go over and see what they are doing. So we went back to Kreuztal, and this is how it was. They had done almost nothing. I would say they had done exactly nothing. So then this was shocking, because at this time, Ueli Weidmann doesn't know this story, he's listening for the first time. But at this time, the building was being constructed. So the whole project was in the air. Nobody was doing anything. We go there, and then it's a shock, because they tell us that there were two of their engineers who knew how to do this, the ones that had dismantled the centrifuge, but they left the company, and now they cannot find anyone in Germany, that knows how to do this. They say, but we found a specialist in centrifuge, and he will come now and we'll discuss exactly how we proceed. So the specialist comes there in Kreuztal. This is we're exactly in front of a centrifuge like this, and you know it's big, it's like 10 meters. So the specialist comes, we're looking at the centrifuge, and he says, "Wo ist die Zentrifuge?" Where is the centrifuge? So then, I mean, I'm really devastated. I have like a nervous breakdown. We get on the plane to come back, and I'm like, Ralph, they are out. Okay, they are incompetent, we fire them, we need to find someone else. And then I think of my colleague Walter Kaufmann. I think he was coming, but something happened last minute that he couldn't, who built this amazing machine, which is called Lucet, which has 100 hydraulic actuators. So I thought, whoever did this with 100 actuators to be able to move and apply these different kinds of loading should be able to do our system. Okay, and this is how we found Hagenbuch, a Swiss company. So Heinrich Hagenbuch, which is here with us today, took over. So Hagenbuch did the refurbishment of the hydraulics, the pump. By the way, the previous company was telling us that we have to replace the pump. It's an old pump, it has an old valve, maybe the valve is not working, but you replace a pump because of a valve. It was ridiculous. Of course, when Heinrich came, he said, come on, what valve? If the valve is not working, we'll make a new one, it's not a problem. So Hagenbuch took over, we were very lucky to find them. They did everything for the refurbishment, not everything, the hydraulics. A big part, however, had to be done after the centrifuge was installed in-house. So March 2020, construction was proceeding. You see here the base of a centrifuge chamber under construction. This is how it was a bit later. So the chamber was constructed outside. As Professor Weidmann said, we used the biggest crane of Europe to install it after it was constructed. And here comes another problem, COVID. The lockdown, you see here, ETH was empty totally. Zurich, you have never seen it so empty. And this is a photo here from Zurich Airport, March 16, 2020. I don't know if you have ever seen the Zurich Airport so empty. At the back, if you look very carefully at the back, you can see some people waiting. This is the flight to Athens. So this is the flight I took. It was the only place of airport that some people were there. Luckily, this did not affect so much the construction. Construction proceeded despite COVID. And this is how the centrifuge chamber looked in July 2020. And a few months later, August 14, 2020, it was installed. You can see here photos of installation by the biggest crane of Europe. You can also see the vibration isolation springs here, these yellow things, waiting for the chamber to sit on them. But because of the various delays and the problems with that German company, a big part of the refurbishment had to be done later, and it was done in-house. And you see here many of the contributors of our laboratory, Markus Itten, Andreas Kipper, Jürg Giger. I have a photo here of an old bearing that was replaced, and I think Ralph has put something in the laboratory like a surprise to see some of the old stuff. The old centrifuge, the way it was, it had a lot of slip rings. The slip rings are used to pass electrical signals from the spinning centrifuge to the outside world. And because it was built in the 80s, everything was analog and it needed a lot of slip rings. Of course, today we have onboard computers, we have Ethernet connections, we don't need all of this. For this reason, it was refurbished and we kept, as you can see here, from all this, we kept 1/3. So what we have today is 1/3, which is more than enough than what we need. The installation of a centrifuge finally happened in April 2022. So here you see it being installed. And still, after the installation, a lot of things had to be done because still it was not ready. You see here some nice photos of Markus and Jürg working on the centrifuge, preparing many of the stuff that had to be installed afterwards. But not only, we also designed a lot of additional equipment that was designed and constructed in-house, like the automated sun draining system that you will see also in the visits. So this system, as you see here in this video, is going back and forth. There is a sun curtain, and with this system we can make models that are controllable and repeatable, which is very important. Repeatability is very important. Also, we made a laminar box. This was designed by Liam Jones. Where is Liam? Liam is in the centrifuge. We will meet him there. Liam Jones, together with Jürg and Andy Kipper and Markus Itten. And this is a flexible box that, as you saw in the video, during shaking it can move. So it allows the soil to deform naturally. It's the only way to do it. Also, an onboard loading system, or a robot, as we call it, which you see it here installed on the acted in shaking table, exactly below. This was also designed and built in-house. And the Actidine saging table, which was supplied to us by our supplier Actidine. I think Didier is here. So Didier. This saging table can be used to model real earthquakes, so we can have accelerographs that we measure in earthquakes and we can scale them down and apply them in the centrifuge. So September 23, the centrifuge becomes operational. This is how it looks. It's a two-story facility. The centrifuge is here at the bottom. At the top we have other things like this. So here at the top you see the connection to the old laboratory of a drum centrifuge is on the left. At the bottom floor we have a centrifuge chamber and the hydraulic pumps that supply the pressure needed to spin the centrifuge. And this is how it looks. So this is what you will see today. The diameter is, actually this number is wrong, is 8.25 meters because the radius is 4.125, which is identical with the one of Cambridge. Right, Julia? Yeah. I don't think it's a coincidence that it's exactly the same radius. The capacity is 5 tons at 100 G, so it is the biggest capacity centrifuge in Europe, like Sasa said, like my centrifuge is bigger than yours. However, the one that Luc has in Nantes, Université Gustave Eiffel, older CPC, has bigger radius. So in terms of radius, Sasa, sorry, but Nantes has a bigger centrifuge than us. But in capacity, we are the biggest. Okay. And I will finish my presentation. I will not speak a lot because we have technical presentations, just with a preview, some research examples of projects that have been completed already. We chose to do the inauguration not immediately when it became operational, but 1.5 years later, so that we have a few things to show. So one of the things we have been doing is related to the retrofit of existing bridges on pile groups. And Labros Akellariavis, who is here with us today here, will make a presentation later. So what is the project here? The project is related to exactly retrofit of old bridges. And these bridges, first of all, as you see here, and this is a real example, you see this bridge here, this part here, what you see, it's stuck. So this part here was installed later to widen the bridge. The bridge only had 2 lanes and then it became 4 lanes. So when we widen a bridge, the weight becomes larger, it becomes heavier, so it needs retrofit. In addition, we may need retrofit for earthquake design because these bridges were designed many years ago, before the 90s, without any seismic design. The question is what happens to the foundation system? Because, okay, the pier, the column, it's something local. You can make it a bit wider. I'm not saying it's easy, but it's relatively straightforward. How do you retrofit the foundation? You need to add more piles. And this means a huge excavation. And you imagine here, in between, this excavation will be here. Can be big excavation to install these new piles. If it's an overpass bridge, you will have to cut your roadway for many months, or maybe more than a year. So this can be challenging, can be costly. So it would be nice if we can reduce this or even to avoid it. Also, in some cases, it's even impossible because when you construct a new bridge, first you do the foundation and then the bridge. So when you have to install new piles, to bring this huge machinery that you see here and install new piles under an existing bridge, sometimes it's even impossible. So we would like to reduce the necessary retrofit measures or even to avoid them completely. I will not get into details about everything that we have been doing. Labros will show you some of this later. A second problem is related to hydromechanical problems, as we call them. And here, this started with a PhD of Liam Jones. I saw here some examples. This is a dramatic example from the Fukushima nuclear disaster, the big tsunami that led to this disaster after the Tohoku earthquake. And in this earthquake, we saw that breakwaters that were designed to be tsunami resistant were totally destroyed. So this implies that there are things that we don't understand. This is why we started this research by building the MTG that you will see. A problem that is very related to tsunamis is scouring of bridges. we have more and more extreme weather events. These weather events lead to extreme flooding, and this may lead to scouring of bridges and failures, like the one you see here from Kalabaka in Greece. The MTG you will see in the laboratory looks like this, and it can model both tsunamis and flood events. This MTG that you see, and you will see when we go to the laboratory, is not yet inside the centrifuge, but there will be a new version that will be inside the centrifuge. It's almost ready, you will see it. And this is how it looks like. You see here the tsunami coming from left to right, overtopping the breakwater, scouring, and leading to the failure of this breakwater. Similar things happen to bridges when they are subjected to flood events and scour. So this is the centrifuge MTG that you will see in the laboratory, almost ready. So when this is ready, we'll be able also to model this inside the centrifuge. And finally, I will close with this. Research we are doing recently related to offshore wind turbines. These are needed for the transition to clean, renewable energy. And there are many problems to solve. And you see here one of the tests with a dynamic actuator made again by Hönggerberg, which can move very fast and model inside the centrifuge 10, 20, 30,000 cycles of loading very fast. So phenomena that take in reality years, in the centrifuge we can do with this actuator in a few hours. So with this, I would like to close my presentation with the acknowledgement of everybody. Hopefully I didn't forget anybody, everybody who contributed. Thank you for your attention, and then we'll continue with technical presentations of more specific things. Thank you very much. I would like to call first Orestis Avamidis, who will show us very, very fast some of the first result of a project Vromos, which was done as part of a project Geolab. It was funded by Geolab. So Orestis, the floor is yours. When you see me standing, it means that it's over.
Okay, well, thank you very much. Congratulations to Ioannis and to the whole team for this great inauguration that we have today. I will be very quick. I'll just present some of the results from a series of experiments we did this summer. I have to say that I think, we were in the first year of operation of the center, so we were very happy that we managed to get all of the experiments done, get interesting results, and we even were here during August doing experiments, which is very rare in Switzerland, so I was very happy that we managed to get everything done. So you saw a video just before of one of our piles. Our project was on offshore monopiles. We wanted to examine what happens with drainage around monopiles during storms. And the motivation is that as we have new generation offshore wind turbines, they become increasingly larger, and that is to minimize the transport and installation cost, and you get bigger capacity per turbine. That means that they need to be larger, they need bigger towers, and they need bigger monopiles. Often these are larger than 10 meters, and in the future they're projected to be even bigger. And the problem is that as the diameter increases, then the soil becomes less drained, and so you might have excess pore water pressures. There's a hypothesis about the dimensionless factor that controls the drainage. So M is a sort of a, in this case, it's constrained stiffness. It could be bulk stiffness. K is permeability. Capital T is the period. Gamma W is the water specific weight, and D is the diameter. So you can see as the diameter becomes bigger, the drainage factor decreases significantly, so you become a lot less drained. That's one of the aspects we wanted to investigate. And then we wanted to see what happens with drainage and also get some results for behavior during extreme storm events, because we're projected to have more frequent and more severe storms. The user team for this was part of the Geolab proposal. So this is a European proposal where you have groups from different countries that can come and use the facility. So we were one of these groups. The user group was us from the University of Oxford, and it was a collaboration with Fugro. And what we wanted to examine for this project was the validity of the dimensionless factor that we have assumed, drainage effects, so what happens with pore pressures, and what happens with monopile response during storms. These are the models we examined. So we have, let me see if this works. No, never mind. So you have on the left a smaller pile. So this is 83 millimeters in model scale, about, it was 50 G, so about 4 meters in prototype. And then we have a 100 millimeter pile on the right. There's a lot of instrumentation there. So you see pore pressure transducers in the soil. And we also have some pore pressure transducers at the pile interface with the soil. And then strain gauges, accelerometers, lasers, and so on. We managed to get 6 tests done. The first 2 were quite quick. They were just saturated with water, slow, monotonic push. And then the rest of the tests were cyclic. So we had displacement-controlled cyclic loading and then force-controlled storm loading. Experiment number 3 is our reference test. So that was the 83 millimeter pile. Experiment number 4 has a bigger pile diameter. Experiment number 5 has the same diameter as number 3, but a higher viscosity for the pore fluid, so a lower permeability soil. And experiment number 6 is the same as number 3, but we have a different loading frequency to examine loading history effects. The way we designed the experiments, because we wanted to see what happens with bigger monopiles, but we couldn't fit a bigger monopile because of the boundaries being too close. We designed them so that the dimensionless factor for drainage would be that of a reference pile of 10 meters, 12, and 14 meters. Well, it was a team effort. Rory Fleminger was the first person you see. This is part of his doctorate. He did most of the work. He was here for the whole time, and he's doing a lot of the process of processing and writing it up. Then I was also here. You can see I'm the only one smiling because I was not here for the whole duration of it, so maybe that's why I'm happy. And then from ETH, we had Thanasis, Liam, and Ralph, who were there all the time helping us to get everything done. This is just an example of what we got for one test. So if it plays, you'll see force displacement at the mud line, moment rotation at the mud line, the 3 lasers on the top right, and what we assume is the shape of the monopile, and then strain gauges and what we think is the moment distribution. And you can see that we were able to get during a storm significant pore water pressures in the soil, including with the PPTs at the pile soil interface. So we're happy that this worked. I think I'm tight on time, so I won't show anymore, but you can see obviously the oscillation, significant suction as well. And we managed to get some results about the dimensionless factor. So these are 3 different tests with the same dimensionless factor. They have different diameters, different permeabilities, and so on. This is an event where we pushed it to liquefaction. You have excess pore water pressure ratio. And in terms of behavior with cycle, it's quite comparable. So we were happy with the dimensionless factor. And on the right is storm loading. We just plot the mean of excess pore water pressure ratio per cycle because there's a lot of oscillation per cycle. And again, comparable behavior for the different diameters, permeabilities, and so on, as long as you have the correct dimensionless factor. But still, we do get some mean excess pore water pressure ratio increasing. It has some effects on stiffness, but this is still work in process. That's all I have. And I hope I was not, Ioannis is not standing up, so I'm happy.
I am now. Thank you, Oresti. I'm sure there are questions, but this will happen in the apero. So now I would like to call Andrea Arnold to show some of the preliminary results of the tests we have been doing together with block foundations.
Thank you, Ioannis. It's a great pleasure to be here and give a short insight on this block foundation project, which is financed by Allianz Fahrweg. This is a joint venture between the different railway companies in Switzerland, and of course is being realized together with the group from Ioannis. Just shortly, why are we doing this project? So block foundation, it's not like a big structure or anything new. You all know them in terms of railway infrastructure. And they are supporting structures for transmission lines, and mostly invisible because they're embedded in the ground. They are loaded mainly by wind, so it's horizontal forces and bending moments. And of course, there is an analytical model, so you can see a part of it in the slide, but it has very limited application as soon as soft soil is involved. And that's why we are trying to get a bit more of details on the load-bearing behavior of those block foundations, especially for soft soils. So that's why we are doing some centrifuge modeling, and there are some first pictures of the last test series. And I want to shortly present how we did the whole modeling. So basically it's lateral pushover tests. And you can see, or you cannot see because it's embedded in the ground, the block foundation. So far it's saturated sand. And we cast them in situ. So we dig a hole and pour some mortar in there, and then we do the whole base detail for the mast. And then we put on the mast. It should be as light-weighted as possible, but you can see later on that there are some problems with lightweight mast. Then, of course, there is the horizontal load on the top to give the horizontal load and the moment, the bending moment. And there are also some measurement systems. Mainly it's laser targets we use to record the movements of the block foundation in the soil. But it's also some DIC cameras to give extra data on the movement of the mast detail and of the top of the foundation. So there are some preliminary results because we did the first test series just some months ago, and we are pretty much in there to look at all the results we got so far. But you can see force, displacement response, so it's the top displacement that you can see, and the force we got, and we are now trying to compare those things with this analytical model and see the difference between what we measure in the test and what we get from the analytical model, which is already there. There is another older test, one of the first tests, and that was with that light-weighted mast, because it's not really good for the whole modeling process to have a very heavy mast, but you can see there on the right-hand side that it was not stiff enough, and therefore the whole load displacement behavior was not really plausible in terms of good results. So finally, I have some impressions for you of the pushover test with the mast after the test was finished, and also of the foundation in the ground after the test. And in the next step, we will prepare some more models in soft soils and also in layered soils. So that would be the next step. Yeah, so this is not Zurich, but Delft, and it was the last physical modeling conference. And clearly this church is no block foundation, but it looks a bit like after a pushover. And in any case, it's soft soils involved here, and I think that shows quite good that it's very relevant to do this research on those block foundations. With that and an impression of the centrifuge, I would like to close my presentation. Thank you.
Thank you, Andre. Now I would like to call Amalia Giannakou to show us some of the first results of the tests of the project Wisdom, or Wisdom.
Well, yes, we call it Wisdom. Thank you, Yanni. Hello. So I'm going to present a series of centrifuge tests also on foundations, monopile foundations for offshore wind farms that we did. We're a design company based in Athens, Greece, but we use advanced numerical modeling for design optimization of a range of offshore and onshore foundations. we have advanced numerical tools that can describe complicated behaviors for sands and clays. And the motivation for this work comes from our experience with the design of offshore wind turbine foundations. The cyclic loading is essentially accounted for with simplified and conservative methods, and we see a lot of room for optimization. However, there is a lack of case studies and experimental data, and it limits our ability to use the tools that we have developed for design optimization, because the more advanced the constitutive model is, there is more need to validate it not only at an element level, but at the system level. So together with ETHZ Zurich, we designed a series of centrifuge experiments to study the effect of the behavior of a monopile foundation under cyclic loads. And this set of experiments was funded by GeoLab. Here you can see the setup. The concept is very similar to what Orestes presented. We're interested in saturated sands. We're interested in cyclic loads with a large number of cycles, varying amplitudes and varying frequencies. And we analyzed both sinusoidal loads and more realistic storm events. Here you can see various photos from the experiments. The sand pluviation, we were targeting 75% relative density. We used Ottawa sand, which is a very well-known reference sand. The installation of the PPTs, the fact that we have a large centrifuge here enabled us to have a dense monitoring and instrumentation, and that creates a very solid database to calibrate numerical models. This is the saturation with viscous fluid, calibration of the instrumented pile that was constructed here by ETHZ. The installation of the monopile, which was done with 1G jacking. And then this is a picture after the end of the experiment where we essentially excavate to study the failure mechanisms. Before we started the test, we have done a series of numerical analyses to guide the experiments and the location of the various PPTs and measurements. We calibrated the numerical model based on laboratory tests on Ottawa sands. And this is an example of a blind prediction of the monopile against a monotonic drained lateral load. And here you can see the comparison with the first test we did here, which was a monotonic test. The red is the test, the black is the numerical analysis, which were in close agreement, and so we're very happy, and it gave us courage to keep going. And here are some results from the cyclic tests. These are sinusoidal loading series of increasing amplitude. And what you see on the upper graph is essentially the increase of in each load packet, we increase the level, the amplitude of the load. On the graph below, you see the increase in rotation of the monopile. And for a specific load level, we see a sudden and abrupt increase in rotation, which was due to the development of excess pore pressures around the monopile, as you see on the graph at the right, which shows excess pore pressure ratio of about 1, where we saw essentially liquefaction. These are more test results. This is for the random storm loading, which is more representative of the high wind of a real storm, again with increasing amplitude, and the rotation of the monopile increases with load intensity. And this is an example of comparison of a blind prediction we did with the red line is the numerical analysis, and the black line is the result of the centrifuge test. And as you can see, there's a very nice match for this load level. To sum up, the facility here and all the new developments, including the actuator, enabled us to do an advanced series of tests and create a robust database for model calibration and validation of numerical tools. And of course, the preparation and the excellent collaboration with the whole group here allowed us to do so in a very short time frame. So we did this series of tests in 3 weeks. Thank you very much.
Thank you, Amalia. Your talk was equally efficient with doing the test in 3 weeks. So now I would like to invite Alexandru Marin, our own Alexandru Marin, to show us some results of a benchmark, a comparison between different centrifuge facilities.
Yes,
It was done as part of GeoLab.
Thank you, Ioannis. Also welcome from my side. The GeoLab project that was already introduced by several of the speakers also gave us the opportunity to create a network of research facilities and to create a community around this network. And as part of the activities of this community, we also did some so-called joint research activities. So this is when we combine our efforts towards a common project. And one of these joint research activities was this paper that you can see here, assessing the repeatability, the scale effects, and consistency and geotechnical physical modeling. This was a collaborative effort between different facilities, ETH, Deltares, TU Delft, Cambridge, TU Darmstadt, Université Gustave Eiffel, and Université Grenoble-Alpes. And all these facilities, they basically try to do the same test and then compare the results of this test and then see whether we have differences, whether we have confidence in our results, and how do our results in centrifuge modeling differ or, let's say, diverge from results at larger scales. The prototype test, if you want, was made in Germany, was done in Germany as part of the GeoLab project. And here we are in TU Darmstadt, in which they have a big excavation pit in which they can install large-scale models. And we're talking here about, if you want to put it on a scale, this would be more like an intermediate scale pile. It's not the full scale, but it's maybe scaled down 2 times or 5 times, depending on the problem studied. And the main objectives of this project was basically to critically assess the response of shared anchor piles. As we move or transition to, let's say, more floating offshore wind turbines, the foundations required to anchor these wind turbines, they start to be shared by multiple turbines. So we would like to see, or they would like to see, how do these piles behave under multi-axial loading, under cyclic loading and monotonic loading. So this was the prototype test. This is the intermediate scale pile, a steel pile which was instrumented with strain gauges and then pushed laterally in one direction, in multiple directions, monotonically and cyclically. What we did in the centrifuge is we wanted to replicate this. So we scaled this down, we scaled the intermediate scale problem, we scaled it to the level of the centrifuge, and then our purpose this time was not in the direction of trying to see the response of the piles, but more to see the consistency, the reliability of centrifuge testing. So we try to evaluate parameters such as model scaling, centrifuge facility characteristics, the way we create our models, the way we test them, then instrumentations, everything based on the results of the intermediate scale test. So what you see here is a sketch of our small scale test in which you can see that we have a pile installed in a layer of sand, which is pushed laterally at this level, and then we have 2 lasers basically measuring the lateral behavior, the lateral response of the pile, and also an LVDT measuring the vertical displacement. The foundation ground is sand. We use the Darmstadter sand. So basically, all facilities received the small fraction. So let's say the sieve Darmstadter sand, which has a diameter below 1 millimeter, and then we pluviated this. We use dry pluviation. We use the automated system that we have to create soil samples which have a controllable relative density, and then we wished in place the pile and then applied laterally the loading using the hydraulic actuator. We did 2 types of loading. We did monotonic loading and cyclic loading, attempting again to see repeatability of our tests, not only repeatability, but also consistency with other facilities who did it independently. And here are some indicative results, some preliminary results. You can see on the vertical axis the lateral force, on the horizontal axis the lateral displacement, and you can see the results obtained at 11G and 17G and then translated using the scaling laws to prototype scale. And you can see on the lower side, you can see the vertical coordinate along the pile height, Z, and on the horizontal side now, the bending moment, which was recorded using the strain gauges. Okay, and then on the right-hand side, you can see the comparison now, the interesting stuff. You can see the comparison between the intermediate scale pile, which is the black dashed line, and then the centrifuge, the results from the centrifuge facilities. So one good news is the consistency that we have between the different facilities. So although we have different ways in creating our models, but when we try to compare models having the same density, using the same pile, we see that our results are very consistent with each other, and this gives us a lot of confidence in performing our research using the centrifuge facilities that we had. Of course, there is some divergence. There is some differences between the intermediate scale pile and the small scale pile, but this is something that we're still looking at. Of course, there's different ways in which they build their soil models. We use dry pluviation, they use dry tamping, they use layered compaction. We don't use layered compaction, so there are multiple factors that can play a role in this comparison. And then at the second stage, after applying the monotonic loading, we relaxed the pile, so we went down to 0 force, and then we applied 2 packages of cyclic loading, a small amplitude package and a large amplitude package. And here you can see basically the bending moments occurring in the large amplitude cycles. And you can see also the accumulation of lateral displacements with the number of cycles, indicating basically, again, the same consistencies that we have observed, and also quite nice agreement with the intermediate scale piles. This would be actually from my side. Thank you for your attention, and also I'd like to acknowledge our colleagues who helped with this project.
Great. Thank you, Alex. Next is Eva Brunsweiler, who will talk to us about monopiles, but monopiles now. Wind farms are migrating to not only to deeper waters, but also in areas of high seismicity and even with liquefiable soils. So the research she will present is related to this subject.
So, hello, I will present to you the Dionysus project, just a very brief introduction. The Dionysus project is an international project with a lot of industry partners supporting it, and Carbon Trust supporting it, and also the Dutch Research Council. Dionysus stands for design of offshore monopiles, including seismic interaction with soil, and is Greek for vibration. Yeah. The motivation for this project comes, as Ioannis said, from the planned locations of future wind farms, which are increasingly in seismically active regions, as, for example, in Japan, Taiwan, and the western coastline of the United States. At these locations, the wind turbines not only experience loading through the wind and waves, but also potentially, additionally, loading through the earthquakes. The difference is that the frequency spectrum from the earthquake loading is a lot broader and a lot higher than for wind and wave loading. So this means that higher eigenfrequencies of the structure potentially be excited. And also with earthquakes is the potential for liquefaction of the soil. If we want to construct cost-efficient and seismic resilient wind turbines, we need to understand the seismic soil structure interaction of offshore monopile founded wind turbines. in this project, we used a coffee modeling approach, so constitutive modeling working together with physical modeling, finite element modeling and engineering modeling with the shared aim to develop a one-dimensional seismic model to design monopile foundations for offshore wind turbines that can be used by our partners in the future. And what's important here, the physical modeling part, which I will concentrate on, is done by ETH and TU Delft. So one of the novelties of this project and the really important part is the scaling of the model. First, and this is rather complex, was done by our partners at TU Delft. We have a complex prototype and we need to simplify it to model it in the centrifuge. And then the prototype has to be shrinked so that the scaled model then fits into our centrifuge. And this, while the dynamic stability of the prototype of the model then is guaranteed, and the nonlinear dynamic system properties and the foundation size are preserved. And the nonlinear dynamic system properties are very important because otherwise we don't have the same behavior of the whole soil structure that we measure in the centrifuge. With this model, we then want to do some centrifuge testing to get an overview of the whole soil structure interaction in seismic events. First, we want to test the monotonic capacity with some monotonic pushover tests. Then we want to have to see whether the natural frequencies of the structure are still the same. This will be done with some frequency sweeps in a water-saturated model that sits in the laminar box on the shaker, and then some earthquake motions will be done with the shaker to get the dynamic soil structure response, both for a drained event, and then with viscous fluid to also see the whole interaction while pore pressures are building up and liquefaction is possible. So we have done some first monotonic pushover tests. Here you see the videos sped up by 100 times because we are doing these tests really slow so that we don't have any rate effects, but then you don't see anything on the video. You see here the top of the yoke system where we apply the force and then also the model line, and on the right the test results we got until now for dense and medium dense sand, showing that in the dense sand we have a stiffer response. So I have to thank now our project partners and the funding we get from the Dutch Research Council and Carbon Trust, which also has a website for the Donesis project. You can see it here with the QR code, and all our partners. And we have a lot of collaborators, which would take too much time to name now, but I just want to thank all of them. Thank you. And thank you for your attention.
Thank you, Eva. Next is Medhard and Rosie, who will show us that centrifuge modeling, what we do here is not only for geotechnical structures, but also for masonry buildings.
Thank you. Hello, everyone. Today I will be presenting about my PhD project in which I am in the final year.
My project is about validation of system-level assumptions in seismic analysis of reinforced concrete and masonry structures through an experimental framework. So the motivation for this research started with seeing the results of blind prediction contest. And here I give an example. So at the University of California, San Diego, this very simple structure, which is only a column with a mass on top, was tested under 6 ground motions. And then a total of 41 expert team from academia and industry were invited to predict the response in terms of what would be the top displacement at the mass. And the winners were awarded, so there was some incentive to give good numerical modeling. And the result for this blind prediction contest was shocking. So on the vertical axis here, I show the maximum horizontal displacement at the top of the column. At the horizontal axis, the earthquake number. The yellow points is the experiment, and all the other points are the predictions of the expert teams. And as we can see, we have very large dispersion of the predictions. Not only that, apparently after the 6 ground motions, the column did not fail, but only 14 out of the 41 teams predicted non-failure. And this makes us question, are we really making the right assumptions when we do numerical modeling? And the answer is apparently no. So how to fix that? We need to do validation, experimental validation, and earthquake engineering. This is on the form of shake table testing. So we have 2 options to do shake table testing, either to do it at full scale or at a large scale. And then we have very, very high costs associated with the facility, with the specimen, instrumentation. Also, we have very long time. One specimen could take up to 6 months in order to test. And the other option is to do that at small scale. And we see that this is very suitable for large data set. Why do we need large data set? Because in earthquake engineering, we have a lot of uncertainties that we need to cover. So one test is not enough to cover all the possibilities. But however, at small scale, we absolutely would need the geotechnical centrifuge in order to preserve the similitude between the small scale and the large scale. However, also at small scale, we have a lot of challenges. It's not easy. The main challenge is construction of the specimen. And here I give an example on the top right. This was a study by Ueli et al. In 2014. She was trying to construct one reinforced concrete column using wires as reinforcement. As we can see, the accuracy was good enough for this study, but was not perfect. In addition to that, it took her around 8 hours of quasi-watchmaker's accuracy in order to produce one column. It wasn't possible for her to produce a reinforced concrete frame because it wasn't possible to put an reinforcement inside the joint by hand. So we built on this study, and we proposed using on the right bottom 3D printed reinforcement. We use selective laser melting in order to produce these very small, very fine cages with very high accuracy. Also for masonry structures, we use binder jetting, which is basically gluing sand together in a very simple definition. However, because we only have one material, we use these notches. If you can see here on the left bottom, these notches represent the mortar joints that we have in masonry structures. Okay, we solved the problem of construction, but it's not only about the construction of the specimens. It's also we need to control the mechanical properties. We need to take into account scale effects, and tension, shear, and bonding. So most of my PhD and also the PhD of previous PhD students in our group, we spent time in trying to control the printing process so that we can control the mechanical properties. And luckily enough, around 1 year ago, I did a centrifuge test where I tested this very simple masonry structure that was tested in full scale in Portugal, and this was the result. So this was a 1989 Loma Prieta earthquake, 285% of that earthquake. And you see at the peak, we have a failure of the wall. This failure mode was exactly similar to the one that was tested in full scale in Portugal. And by understanding how these structures fail and how they behave, we're now able to better calibrate our numerical models and better design our structures. Thank you.
Thank you, Medhat. So these little houses are like this big, and the results are the same with a big experiment in the shaking table. And you were able to do, if I remember correctly, 30 tests in 1 week, right?
Yes, 15 days.
So there are huge advantages of doing this in a centrifuge. Last but not least, from the technical presentations, Labros Akellariadis, who will talk about the work on pile groups.
Thank you very much, Yanni, for the introduction. I would also like to welcome you from my side in this last presentation of this session. I think I could go quickly through the motivation. It was already covered by Ioannis previously, but just keep in mind that we are looking at old existing bridges founded on reinforced concrete piles that today, as they reach their lifespan, either due to retrofit needs or our desire to upgrade them, we have increase of loads transmitted to the foundation level. And what we try to answer is whether the pile group retrofit is really something essential. We tried first to answer this question in the old drum centrifuge of ETHZ, and considering that adding more piles next to an existing foundation is a pretty challenging operation from an engineering perspective, we decided to re-evaluate those retrofit needs experimentally. And we created very simple physical models of those two cases, the initial and the retrofitted bridge, founded on the same pile group. And then we place them and we test them at the ETHZ drum centrifuge, applying lateral loading. And you see some videos from those two tests. And moving on the results from those experiments, we will find out that the very same foundation, when it supports the heavier retrofitted bridge, it can actually mobilize considerably higher moment resistance. In other words, it is stronger. So if it is stronger, why should we retrofit it? Why should we add more piles? It can be slightly more complicated than this, but the big picture is there. We have a big incentive to rethink and improve our engineering calculations, especially when it comes to evaluating existing old foundations. Episode 2, testing in the new beam centrifuge of ETHZ. Like every sequel, let's start with a very brief recap. I told you that we are focusing on reinforced concrete piles. Reinforced concrete is a composite material made of concrete and reinforcement. Reinforcement detailing will control how those piles yield and eventually fail. And if we look at piles that were constructed more than half a century ago, we will find many examples where the reinforcement will be inadequate with the standards that we have today. So when the new facility opened its doors, we went back to revisit the same problem, the same piles under the same conditions, but this time, thanks to the increased capacity and capabilities of the new facility, we had the opportunity to have a way closer look. We could do things twice as big and reach a level of detail that it was not possible previously. Like what Matt had just presented, we created miniature reinforced concrete members, building on some excellent existing work, made of 3D printed steel cages and a mixture of cement and fine-grained sand as scale aggregates. What you see in this video is that we did many trials with Anastasopoulos and Simone Albert until we made sure that those miniature members resemble our target features of the prototype real-scale ones. And once we were sure that they do so, both for well and for pool reinforced concrete members, we were ready to move and test them in the centrifuge. We have created our models with the pluviator that you see in this photograph. We have installed our piles. We mounted our newly developed loading apparatus, and we were ready to start spinning. And we tested 3 different cases. We tested a well-reinforced pile, like the one shown here, a pile that could be designed today, particularly to resist high lateral loads. Another pile with very minimum reinforcement, like some examples that we find from engineering reports from the very past, and also an intermediate case that is actually the most representative example. And pushing those 3 systems laterally under fixed conditions, we documented different failure modes. We see that the piles fail from a very ductile flexural mode to a way more brittle shear-dominated one, depending on the reinforcement detailing. And this reminds us that structural details can have an important effect, especially when it comes to very old foundations, and this is something that we should keep in mind. Time to wrap it up. We do think that we can have significant savings of resources, of environmental costs, but also of traffic loads if we avoid unnecessary retrofit of existing foundations. But for this to be possible without compromising safety, we need first to rethink and improve our engineering calculations. And in this direction, we use our centrifuge observations to develop guidelines and tools that could find their way to daily engineering practice. We have proposed guidelines on how to perform either very simple hand calculations or way more complicated numerical simulations and evaluate the retrofit needs of any pile group layout under any soil conditions. Those two approaches differ considerably in most aspects, but they have something very fundamental in common. They were both driven by our centrifuge test observations. They were formulated in a way that they could reproduce successfully the trends of our centrifuge test results. And today I have shown you only 5 tests performed in the drum and the beam centrifuge of ETH. During this work, we have performed actually more than 55 such tests. And at this stage, I would like to thank the Swiss Federal Roads Office and the Swiss National Science Foundation for financially supporting this research, but also my many good colleagues for contributing in various stages of this work, making those experiments possible. This brings me to the end of my presentation, and I would like to thank you all very much for your kind attention.
Thank you, Labro. Episode 1, episode 2, usually it comes in free, right? So what is episode 3? We need to see. Okay, so this brings us to the end of the technical presentations, but it's not the end, because now we will attempt something that we have not attempted before. We will run a centrifuge test, a trial flight, let's say. It's not a trial because we have been using it for 1.5 years, so it should work. Hopefully. So we will do a flight and we'll have a surprise for you. It's not an experiment exactly, but it is kind of an experiment. So let's turn on the centrifuge first. Can you turn on the centrifuge? Ralph and the guys are in the laboratory at the moment, so we'll have a live broadcasting. Okay. So the lights at least work. So now we'll connect with broadcasting to see everybody who is there, preparing. Hello guys, can you hear us?
Hello, we can hear you.
So, from left to right, we can see Liam Jones, Ralph Herzog, Jan Lauer, and Marcus Itten. So because the whole idea of the whole endeavor came from Jan Lauer, I had promised to Jan that today he will be the one who will press the button. So Jan is there, waiting to press a button. I give it to you, Liam.
Thank you. So, we are first going to start the centrifuge, and while we are spinning up, I'm going to explain exactly what's going to happen. So, Jan, press the button. Excellent. So, what's first going to happen is we're going to start the motors of the centrifuge itself. These are the 2 hydraulic motors. You might be able to faintly hear them click on in the background. You are connected right now to the audio system of the centrifuge. Okay. As is nothing like this. Cool. Everything was good, so they'll take just a few seconds to click on. Okay, so on the right of me, so over there, and on my left, you will see 4 cameras. So on the top left, what you see is our top view. Here. A top view of our dynamic actuator setup. Okay, and below that, you see our victim for today. So what we're going to do is we're going to push this very nice bottle of champagne into one of our test baskets. So you can see inside the test basket in the top right of that screen there. So that's now looking down inside the basket. The bottom right screen is showing you video inside the centrifuge chamber itself, and you'll be able to see the centrifuge screen and as we go. Okay? So, as you can see, the centrifuge is now started. So we're slowly going to spin up to our target level. I hope everything is still connected okay. Yep, good. So we're slowly spinning up now, and what we're actually doing is we're checking out the imbalance of the centrifuge itself by monitoring the displacements of the whole chamber. Because we have an isolated chamber, we can actually see how well balanced the centrifuge is by how much the whole building moves. So we're now checking this to make sure that we have a reasonable imbalance, and once we get to the target speed, and the imbalance is okay, then we'll be able to start the test. So you can see now on the top left camera, the basket itself rotating out. And now you're starting to look down on top of the test itself. You see towards the top of the screen is our actuator. That's the thing that's going to push the champagne bottle. And you see below the silver box, which has 101 written on it, is our high-speed camera. So we're going to push the champagne. You're going to see it fall in real time, and I'm going to video it with the high-speed camera, and hopefully we can watch it back after at 6,400 frames a second, or roughly 200 times slower than that.
So, Liam, you will let gravity, centrifuge gravity, to smash the champagne, right?
Exactly. We will use the centrifuge hypergravity, as we like to call it, to smash the champagne. Okay. So, what speed are we at, Frank? Okay, so we're still spinning up. It's going to take just a minute longer. You can see we don't need very much G to do this test. We'll only be operating at around 20 G. So you see the centrifuge is very relaxed at the levels. No stress. Can't say the same for any atmospheric controller, but centrifuge is set to flight. Okay, so what you see in front of me, on the top, generally we have the monitoring on the centrifuge itself. So here we have both the onboard cameras, which are the things you can see, plus we have all the external security notifications. So this is where we can check if the centrifuge is going well. So we can see all the important connections, as well as all the doors and the exits to make sure we are safe. In front of me here, we have the control of the actuator that's going to push out the champagne. And over on the far right with Marcus and Jan is the active control of the centrifuge itself. Okay, so Marcus has given me the thumbs up, which means we're now at target speed. The first thing I need to do is to arm the ISD camera. So I'll just do that. We're using an optical trigger, so the camera itself is going to look for the falling bubble and it's going to trigger itself. Is the idea.
Okay, so this is that worked. So I can just
go. The camera now is calibrated to itself. Okay, so now it's ready to go. Okay, so we will be ready to test. I think everything looks good, the balance is good. Everyone is happy? Excellent, so now we can begin to push the bottle around, please. So you will see in the bottom left, bottle is being slowly pushed out. And you might hear a very loud bang, so I apologize for that if it's very loud. It may make you a little bit more possible. And it's about to go. That's it. The centrifuge is officially inaugurated. Okay, so give me just a second, I can try and recover the high-speed footage. Okay, so this looks good. Now I can switch and share the screen.
Can you show slow motion?
Yes, just give me 1 second. Okay, sorry, let's try again. Okay, here's the recording. We hit play. And here we are, this is now 400 times slower. It's quite impressive.
Good.
Fantastic.
Liam.
So thank you very much to Everyone here?
Liam, try to clean it up before we come for the lab visit, okay?
Thank you very much. I'll hand it back to you, and we'll see you soon.
See you soon.
Thank you.
So thank you all for being here with us in this very special occasion. It's not over. The apero starts. So we go to the apero, we have some time together, and then we'll start doing the lab visits, which will be per groups of 25 to 30 people. Thank you very much.